We are the Aero Aggies. Our aircraft is the New Intelligent Communication Kinematic, or the N.I.C.K. The project we undertook this semester was designing a high-altitude, long-endurance unmanned aircraft. The mission of this aircraft is to deliver wireless internet access to remote areas using laser-based communication systems. We were challenged to meet design requirements of flying for at least a week with no refueling, flying above 60,000 feet, taking off and landing on a standard runway, and carrying a payload of at least 220 pounds. Our team wanted to meet these mission requirements in a cost-effective, efficient, and practical manner. As stated, we met the design requirements, and our final aircraft had specifications of a gross takeoff weight of 2,020 pounds, an aspect ratio of 21.4. Our wing loading was calculated to be 1.9 pounds per feet squared, and using drag estimates, we found our cruise speed to be 120 knots and our maximum speed to be 175 knots. The N.I.C.K has a maximum power available of 40 horsepower. Our wing had a taper ratio of 0.75. These design decisions were determined through analysis and comparison.
2D aerodynamics. After analyzing various airfoils found online at the UIUC Airfoil Coordinates database, we selected the SG6043 high-lift airfoil for our wing and the NACA 0010 airfoil for the tail. The SG6043 has a maximum ratio of liftover drag coefficients of 175 at our design cruise Reynolds number of 1 million and angle of attack of 2.2 degrees. This ratio is what we focused on when selecting an airfoil. From the polar plot, you can see that the lift coefficient at the angle of maximum liftover drag is 1. The high moment coefficient of this airfoil meant that a tail had to be included in the design, but the exceptionally high ratio of liftover drag coefficients, along with the increased stability of a traditional wing and tail design, was enough to justify this addition. Aerodynamics and control. The main goal of the aerodynamics group in this project was to minimize drag of the aircraft and therefore minimize power draw. This is essential for a solar electric aircraft such as this, which is limited in endurance by battery weight and solar cell efficiency. The zero lift drag condition was estimated by taking the component drag coefficients, multiplying them by their respective reference areas, summing the results, and dividing by the total wing area. This resulted in an estimated overall zero lift drag coefficient of 0.0075. Substituting the drag estimate and the estimated overall lift coefficient from XFLR5 analysis into the overall drag equation, CD equals CD naught plus KCL squared, gives an overall lift-drag ratio of 34. Our tail was sized to make the aircraft easy to control with minimal input, because level flight is the best for both aerodynamic efficiency and solar energy collection. The V-tail was designed with a horizontal tail coefficient of 0.43, while a smaller horizontal volume coefficient would result in reduced drag. The large moment produced by the wing and the lack of flaps on the wings necessitated the larger control surface on the tail. The vertical tail volume coefficient is calculated to be 0.36. It is ideal to have a large vertical tail coefficient for this aircraft because the aircraft has to loiter for over a week. The large vertical volume coefficient will allow the aircraft to stay level while loitering without having to use ailerons, while minimizing the risk of flow separation over the tail, which would cause a large increase in pressure drag.
Next, we have the propulsion system. Our choice of motor was a 13 horsepower electric direct drive motor that has been used for several experimental planes. Using the drag estimates, we were able to plot the power needed for all realms of flight. We then opted for a 4-motor configuration. This gives us more tolerance in all flight regimes, but more importantly, it allows us to evenly distribute the blown area across the wing more efficiently. Also, we can run each motor at a lower RPM, thus consuming less power. Because we will be cruising at a lower RPM, we opted for a large 2-blade propeller. This will give the plane sufficient thrust at takeoff and operating speeds. The most efficient batteries on the market happen to be the larger batteries. However, they did not produce the correct amperage or voltage to sufficiently run the motors at a decent weight. Thus, we went with a setup similar to that of Tesla batteries. The N.I.C.K uses a total of 22,000 lithium thionyl chloride batteries. There are 20 batteries in each bank and 1,100 total battery banks. In order for the batteries to reach maximum operating conditions, there will be 2 low amperage heaters incorporated within the wing to optimize the battery temperature at cruise altitude. Looking for solar panels, weight was the biggest factor. We picked an organoid halide perovskite solar panel that is still in testing. At only 12% efficient, it is not the best, yet it makes up with its weight. Covering the entire top surface of our plane only resulted in a 10-pound increase. Half of the batteries will be concentrated in the wing closer to the fuselage to reduce wing deflection. In order to obtain the needed center of gravity, the other half of batteries will be located in front of the fuselage. The motors will be mounted 6 and 30 feet from the fuselage. During optimum sunlight hours, the solar panels will be charging the batteries and powering all 4 motors. During dusk and dawn, the solar panels will only be powering the motors. As the sun goes down, the motors will be entirely powered by the batteries. If the batteries do not become fully charged during the day, they have several hours of tolerance to make it through the night. If the batteries are charged below the threshold, the plane will slowly descend until it either lands or starts charging again, in which it will return to cruise altitude. The N.I.C. will use maximum power to climb to 65,000 feet, which takes just under 3 hours. The line on top of the chart represents the power the solar panels provide during the day. On a full charge, the N.I.C. can fly up to 16.4 hours without any sunlight at cruise speed. If the N.I.C. is deployed at night, it will climb at max cruise and then dial down to cruise for a time of 14.9 hours. If conditions cause the plane to speed up to max cruise conditions for a long period of time, it can do so for roughly 10 hours. These calculations take into consideration all sources of power consumption. Structures and materials. The chosen aircraft design relies on a main carbon fiber spar in front of the wing with a smaller carbon fiber spar at the back of the wing. These 2 spars have 15 wooden airfoil ribs around them for each wing. The fuselage is comprised of 9 circular wooden ribs connected by wooden stringers. The chosen tail is a V-tail design made of a hollow piece of wood. Everything except the tail will also be covered in a very thin layer of fiberglass skin. The entire structure weighs about 540 pounds.
The payload for our aircraft is the NASA-designed Opal system. This optical payload for laser comm science uses a laser to transmit data from altitude to Earth. The system lasts for over a week and weighs a total of 220 pounds. It transmits data at a rate of 50 megabytes per second and requires 120 watts of power. The flight system on board the N.I.C. is responsible for tracking and flying the aircraft in any situation. The system uses an onboard tracking system that transmits the flight information to a ground system to update the plane's status. The ground system also transmits information to the plane to update the plane's mission directions. We used a pre-existing system for our autopilot. This autopilot is commanded by a ground control software that supervises 4 servo motors on the aircraft. These servos actuate the control surfaces, the throttle, the landing gear, and any other component that needs input while in flight. Our retractable landing gear design consists of 3 wheels, 1 wheel on each wing and 1 on the rear end of the fuselage. Using aerodynamic, structural, and propulsion parameters, the team was able to analyze the performance of the design. Thrust and power plots were created, as well as a plot for rate of climb at sea level and at altitude. A flight envelope was also determined. After determining our cruise velocity, we were able to calculate our level turn radius and our level turn rate. Next, the minimum takeoff distance was determined to be 1,614 feet. Our minimum landing distance is 1,625 feet. The maximum range speed for our design occurs at the bottom of the power required curve. The maximum endurance speed occurs at the bottom of the thrust required curve. The maximum rate of climb is equal to the maximum excess power divided by the aircraft's weight. As the plane goes up in altitude, the rate of climb decreases. When the rate of climb is equal to 100 feet per second, the aircraft has reached its service ceiling of 88,000 feet. Each component of the N.I.C. was broken down and analyzed in order to find the final weight of the design. Total propulsion weight was 901 pounds. Total structural weight was 538.5 pounds. Using fiberglass and paper-thin solar panels, the skin weight is 215.2 pounds. The system adds up to 135 pounds, and adding gives an overall weight of 2,020 pounds. After iterating through different wing locations, the optimal center of gravity was found to be 10.5 feet back from the tip of the nose. The static margin was found to be 6.83%.
Here is the 3-view display of our final aircraft design. Were we to take this fully to production, there would be certain design decisions we would change, such as fuel usage or more in-depth structural analysis. However, overall, we believe we have met the design requirements and designed an aircraft that our team can be proud of.